I have not many students. Why? Let's wait for 5 minutes, 3 minutes. Okay, let's start. So, the previous lecture we obtained Friedman equations. Today we will speak about this. We also discovered that that really, if we will consider the one of the Friedman Lemaitre equations, this one, so we can see that if we will compare it with with Newtonian case, it really looks like similar in the sense that we only need to change, instead to consider curvature of the space, we need to put total energy like this. So also we discovered that as well as for a Newtonian case, here in relativistic case, we obtained the three model principle. We can see that it should be three model of the universe, which correspond different, and we will come back to this. So this is space with a negative curvature, positive curvature, and flat space. We can say here that exactly for if we will ask the question, but which is really curvature in our universe, it's exactly correspond to the case at k equals 0. So the space in our universe is a flat, and exactly it's correspond to the conditions that energy density, the mean energy density in the universe, is equal critical value, which is really looks strange, because we calculated and we can see that this critical value is limit for the energy density, which we obtain directly from our equation. So we didn't invent anything. It's depend only of Hubble constant if we calculate it for the present time, and it looks like really miracle. Why the universe such a way that epsilon equal epsilon CR? So exactly this value. Again, it looks like somebody tell God would like to make the universe like this, but we are a scientist, so we need to find the answer on this question too, and we will find it a little bit later. So also today, our next step, what we would like to obtain. So we would like to obtain the evolution of the universe. And when we speak about the crucial value which can tell us about the evolution of the universe, this is scale factor. So the final goal, this is to find the dependence of scale factor on time. And in this case, we will understand how the space and how the universe evolve, in which law in the future, and how it was in the past, and to try to coincide this with observational data. But before to jump in this problem, and solve the equation and to understand how we can solve it, in the first, I would like to do attention on to come back to Einstein equation. To discuss some special things which is related with to Einstein equation. With lambda term. So because when we will speak about matter which distribute in the universe and which really can influence on the evolution of the universe, we will see that we will need something else, not only the matter which we understand well, I mean baryonic matter or even dark matter, also radiation, but we will understand that we need something else. Why this point is important. From another point, it's also important because да. So to understand how appears this lambda term, which is famous because it was considered as a big mistake of Einstein. We need to come back to the idea how we can obtain Einstein equation. The proof which I gave you was like much more physical consideration. So we go from Poisson equation for gravitational field, and we generalized it for a relativistic case. The second possibility, and which is much more, I'll call it precise, I would like to say. So this is to obtain the equation of gravitational field from the variation of the action. So in this case, as we for example, used the same in classical mechanics. So we can obtain the gravitational field from the condition that variation of action equals 0. The problem to construct the action for gravitational field. And I will tell just a few words about this to show what is the problem, and also it is important not only to speak about this magic lambda term, but also about some alternative gravitational theory. So the idea is the following. We can put here, we understand that when we need to consider the variation from the action, we understand that it should be variation of, it should be the action, the total action is the sum of gravitational action plus action of the matter. the matter much more understandable. So we have only, as we consider it, stress energy tensor, which we in principle understand how we can involve in action in gravitational equation. About gravitational action, so and you remember that to find the left part of Einstein equation, when we proved it from general consideration, you remember that it was not so simple, because, for example, we need to know, and by chance, there is really this beautiful differential Bianchi identity, which allow us immediately to see what should be the left part of Einstein equations. This is Einstein tensor. So when we speak about action of gravitational field, we need to go from general principle of general relativity. Sorry for Colombo. It means the main idea of general relativity is that all coordinate system or all reference system are how call it, we can the equation should work in any reference system. I can say like this. So they are in equal conditions, I mean, reference system. To do this, to satisfy this condition, and this condition is understandable again, because this idea that why we have a good equation only in inertial system, which is related to special relativity, and the idea of Einstein, we need to find the equation which will work in any reference system. So to satisfy this condition, the action of gravitational field must be scalar. So it means that when I write the action of gravitational field, I need to write like this. So this is an integral from Lagrangian. I will put here gravitational, okay? So multiply on element or for volume. I didn't give you this proof what is element of for volume, because we didn't have enough time to succeed with everything. But the for volume, if you have a metric, so we need to put here my square root minus g. Sorry, some question? No? Okay. D for x, where g, this is determinant of GIK. So why we put under square root minus, so don't be, it maybe looks strange, but we need to remember that we choose the signature such a way that the signature plus minus minus minus. So the final value, when you will find determinant, it will be negative. I need to put here minus. So this is so-called, in principle, when we put to be precise here in such a kind of four-dimensional time space, four-dimensional time space, okay. Lagrangian, we of course we need to speak about Lagrangian density, but for now it's not so important. So we can speak about Lagrange. The main problem and the main goal that the equation, what is exactly this Lagrangian density, Lagrangian? What we need to put in our equation to satisfy these conditions that final equation must work in a reference system. And it means that Lagrangian must be also scalar. And we need to find, and we need to clarify and to understand what is this scalar to describe Lagrangian, which describe gravity. Since we agreed before, and we spent a few lectures about this, that now the gravity is a curvature of the space, it means that it should be something which describes the curvature of the space. Some value, or some object which is scalar and describes the curvature of the space and contains information on the curvature of the space. In this case, we immediately understand that it must be scalar curvature. So this is scalar, and this object consists of information of the curvature of the space. Of course, we can ask question, and this is exactly what Einstein was used, and this action called also Einstein-Gilbert action. So you can consider exactly the integral of r minus g d for x. And of course, we need to put here some dimension multiplier because we want finally to obtain the equation in dimension form. And it means that, for example, if you would like finally to have to measure the mass in gram, so you need to take into account here some term, otherwise it will be a problem. Yes, and also we need to put here minus, but it just you will see that it should be if we will prove everything. So finally it must be like this, c cube 16pg. As again, we understand why we have here 16p. In any case, it's related to the 4p, 4 pi g, and again we understand that this is related to the Poisson equation because we need to take into account that in limit case it should be correspond to classical mechanics. So usually, sometimes I give this proof to obtain from variation of Einstein-Gilbert action to obtain Einstein equation. But now I just want to show some special things in this case. So, and after this, you need to consider. So this one plus s matter equals 0. If you will do this properly way, taking into account the results from the tensor analysis, you exactly obtain Einstein equation. So it's not obviously r equal 8p GC4 T IK. So this is correspond if everything will be made is the right way. So finally we obtain Einstein equation. This is another proof. You can look in Landau Lifshitz, but as usual, you will find the place like it's simply to see, which is not so simple. Why I decided to do attention on this? So you will obtain the point that you will obtain Einstein equation in this form if you exactly consider as a Lagrangian density the scalar curvature, like this, in this form. But we can also ask the question, but look, okay, but we can also to put some constant. And in principle, Lagrangian, we can choose a Lagrangian up to some constant. And in general case, in constant, actually, some constant is also scalar. And we can consider the possibilities that how it's better to write. Okay, I will write like this. With Einstein, Hilbert action, proportional. I will put like this. I don't want to write this constant of integral, and I can write like this: r plus lambda some constant minus g d for x. So it's not such a kind of things which we let's invent something else. In principle, it's a much more general consideration. So we need to put some constant. Of course, this creates additional problem. And Einstein, when he worked with the equation for gravitational field, he didn't want to take into account some constant, because we try all the time when we build this theory, we try to avoid the possibility to introduce the new values, which should be like a fundamental. So we are happy already. We have a speed of light, we have a Planck constant, we have a gravitational constant. So it's enough. As soon as you start to involve something additional, you need to, to make some additional relation with additional constant, which is not beautiful. All the time we try to avoid it, as well as we try to I would like to say the better theory is a theory which, or simulation, or like this, or model which use much less parameters. Some question? No, okay. So, but in any case, finally, Einstein decided to put this constant in equation, even after the point, after this, after the formulation of general relativity. Why? It was related exactly with the problem that when general relativity was obtained, the equations. For this time, it was 1915, 1916. We know a little about global properties of the universe. For Einstein, universe should be static, and nothing shows that that universe is really dynamical object. He understood that as soon as he will put this constant, as soon as you consider only this summand, this multiplier, the scalar curvature, the universe will be evolve and will be not a static. And to save the static universe, he decided to put in gravitational action, and now we call it lambda term, or we also call this as a cosmological constant. We will see that the problem, and we will consider a little bit later, the model of universe, the static model of the universe, which Einstein considered. The problem was that when he decided when he put this constant, And we also will see what it will happen with Poisson equation, because it's understandable that in Poisson equation we will also have this lambda constant. Of course, it's also understandable that it must be very small value, but it exists. Now, when he apply, when he consider, and the cosmological constant, as we also will see, create something like anti-gravity. So it looks like against gravity. Why it was idea to use it to succeed with static universe. Really, he for a while succeeded with a static universe, but he immediately could see that to put to use this cosmological constant, in any case, universe will be not stable. So it's like unstable equilibrium. So if a little bit the energy density will be changed in some volume, so the universe, in this case, is equilibrium will be not satisfied, and universe in any case will become dynamical, so non-static. Why here we know this famous words of Einstein, so that using this lambda term is the biggest mistake in my life. And for a long time, it was really like this. Only in some books, there is great books during 20th century, cosmological books, including famous Soviet cosmologist as Zildovich. In any case, they considered these models with lambda constant, which was strange, and we will see what this lambda constant can describe. But it looked like just a play. Okay, let's consider what it will happen with this strange term. Now it's this cosmological constant play a crucial role to explain the observational data and to explain the acceleration of the universe. So, and this is like a bright example when you think sometimes that you made a mistake. Maybe this is not a mistake. Maybe this mistake can be really something important in the future. I speak about science, of course. So this is, and also since I already next to this Einstein-Hilbert action, you also can ask a question, but okay, we need to put here the scalar, but why we put exactly only scalar curvature in the first part? So in principle, we can, instead to consider R, we can put, I will like this, some function of scalar curvature. It's, of course, also satisfies the main principle of general relativity. It's the scalar, it's some combination of scalar curvature like this. And this question is really right and important because, yes, we can put, for example, r squared plus r plus lambda. It looks like the Einstein equation is a form which we know very well and which obtained from the idea that we put in Lagrangian density scalar curvature. It's only one possibility. And it looks even like, one term in the series. And nobody can say that we can't consider this some function of scalar curvature. And really, there are such a kind of series, models, and which call F F from our gravity. So this is exactly, you know, the point why it's important to prove everything, because in this case you understand which suggestion we put in the beginning to obtain the final result. F from our gravity is also important, and also they predict something which, for example, can be different from only consideration of scalar curvature. And also I would like to say that F of our gravity play essential role for explanation of the early time, the time which is related with the first, how call it, the beginning of the burning of the universe. So the inflation model, which we will consider later, is related and can be described also some of the particular case of F of our gravity. So this is just what I wanted to say about Einstein equation and some special cases. So, okay, now now I will come back and soon we will see how this lambda term considered to describe evolution of the universe. Now I want to come back to Friedmann-Lemaitre equation. So, and to discuss how we can solve it and finally to solve it. So Friedmann-Lemaitre equation, again, I will remind you. Friedmann-Lemaitre equation. Okay, let's write it here. A.8 will be useful for us to have it next to us, right? So I just, yes, so I repeat this equation, and yeah, and what is important, I can put here the lambda, the summand with the lambda term. So if, for example, we will solve the equation with lambda constant, we need to, and it's understandable that it need to appear in the Einstein equation. And this will appear here. I will put it with some with color. Plus lambda divide on 3. We even, of course, it's better to solve the equation, but we even can understand why we need to have here this 3 in denominator. Because as here, you remember, we obtain it here due to the fact that we are working with 3-dimensional space. And this 3 also appear here. We also need to be sure that we put the summand with right dimension. So, and it depends on the fact how we put here the lambda constant. If we will put it in Einstein-Hilbert action like this, so it means that dimension of lambda, this is dimension of scalar curvature, and this is 1 divided on L square. Okay, because we remember that scalar curvature, which is swapping of Richard tensor is swapping of Riemann tensor, and this is the second. This is derivative of Christoffel symbol. So, and this is 1 divided on L square. So, but now we can see that here dimension, we remember 1 divided T square, and here we have 1 divided on L square. It means that we need to use speed of light to, you know, to satisfy this dimension on the left part of Riemann-Lemaitre equation. And we need to put here c square. In this case, we have exactly dimension what we need. Okay. So this is Riemann-Lemaitre equation taking into account lambda constant. This is one of the Friedmann equation. The second Friedmann equation, which we also call equation of acceleration, will look like this. Okay, I will put here blue. A point divided on 8, equal minus 4 pi g divided on 3c squared epsilon plus 3p. This I write. Let's check that it's right. Where's equation for? Yeah, this one. So this one. Okay. So I come back. And again plus, okay, put it in green, plus lambda c squared divided on 3. So the summand, this summand will be the same for both Friedmann-Lemaitre equation. And in principle, you already can see that there is can be such a play, you know, between the term which consists of the lambda term and also the energy density, so which is related to the fact with which matter we will consider our universe. We will look on this in detail. Okay, for Friedmann-Lemaitre equation, let's write here with cosmological constant. The term. It's we agreed to use for this term the letter lambda, big lambda. So, and when we say about lambda term in Einstein equation, immediately everybody understand what about we are speaking. Okay. So before to see how this lambda term play a role to create a static universe, why it doesn't work, and how it will work for to explain the observational data and acceleration of the universe, we need to come back in the first to understand how we can solve Friedmann-Lemaitre equation. Is it enough what we have, or we would like to have something more? Yes, we would like to have something more. When we look on this equation, in the first we can see that, yes, our goal to obtain the law for scalar factor, which is a function of the time. But also we can see here that we have also energy density, we have pressure, we have sign of the space. So, and the two equations are not enough to solve this problem. We need something else. And now we will obtain additional equation, which for us will be very convenient to consider, because this equation will allow us to see, to find the relations between scalar factor and pressure and energy density. So to do this, we will use the first law of thermodynamics, and the first in the form. So first law of thermodynamics. So it means that we can write that dE, where E is energy, total energy of the system. This is T ds minus P dV, where E is total energy of the system, T is a temperature, S this is entropy, and P is pressure, where it's volume. So now we can put some somehow call it some discussion of this point of our system, which we consider the system which we consider this is universe. And the point is that when we obtained the not only this universe and gravity, when we obtain the gravitational equation and apply it in the universe, we, in principle, we consider that entropy is a constant. So why? Because, for example, when we used the expression for the stress energy tensor, we used it in the form, you remember, UK I minus delta IKP. Okay, what it means to consider the stress energy stress tensor in such a kind of form, we ignore completely the effect of dissipation of energy. And exactly the dissipation of energy bring us to the increasing of the entropy. In principle, yes, you can say that, but we, of course, in much more general case, we need to take into account these things. But we can agree with that maybe this is also important, I mean the dissipation effect, considering such a kind of system, because if we have a dissipation, of course we need to put here some additional summand which are related to this things. But we can consider that all these effects which are related with the dissipation of energy, they important on some value in some regions, and they're enough small with comparison to total energy density of the system. So, and in principle, this effect will not influence so much that we can really ignore it, consider it the evolution of the universe as a whole system. So this is a trick. Of course, as usual, we would like to simplify the system when we consider really complicated system, and this is a general procedure. So we try to consider more simple system and to obtain the global properties. But of course, we need to control that we can do it. In this case, we can do it. Really, the change of stress energy tensor due to dissipation effect will be so small that much more smaller than total density, energy density of the universe. I mean, we speak about the energy of the rest energy of all material bodies which are located in the universe. So this is the point. So all these words I say to just to justify that we consider the system with a constant entropy. Of course, all time, but we need to remember about this. We also maybe for future. We also understand that in principle, when we consider the universe as a huge scale, so It can be also the change of the gravitational fields, change of the metric of space and time. And in principle, in this case, it should be also taken into account. But for now, we can consider this more simple consideration, and since it can be not influence on the global evolution of the system. So finally, I finished to speak, and now we write what we will obtain. If S equal constant, so we have only dE equal minus, or let's write like this, plus B dV equals 0. Okay, from this equation, we obtain this one. So, or if we will divide on dt, so we can just put as usual is as well as soon as we put point, it means this is derivative by t plus p point equal 0. Now let's again consider some volume with a fixed radius which corresponds to the present time, t equal t0. T0 as usual, as soon as I put 0 as index, immediately understands that I refer it to the present time. So, and we choose a volume with this radius, but we consider this volume will evolve corresponding to this cosmological principle. So, which we all time to put to obtain our equation like this. Okay, so we involve here scalar factor. I mean, immediately understands that we put it due to the fact that the universe is homogeneous and isotropical. So since we can write here that volume will change, it implies spherically symmetrical things, so it will be just the volume of the sphere. Or since we need here to put derivative of the volume, so I consider that v point equal, I will keep this one, and here I will have 3 a square a point. Okay, and I will do like this. I want to keep the volume, so I will put here cube divide on a. And in this case, I will have here this one, and this one will be again volume. So finally, I will have 3 v a point divide on a. So the inner energy of such a kind of volume we can write as because we need also to put, you know, in this equation the point. We can consider, and it's a function of t, as a volume which change the time multiply on energy density. Okay, so from this we can write that E point equal, so V epsilon point plus V point epsilon. And since we have what is V point, if we put it here, we will obtain, so we can take out V outside of the brackets, and here we will have E point plus 3A point divide on A. Sorry, epsilon also. Epsilon. So if we will put all of this in this equation, let's call it like a star here. Put it in star. So what we have? We have E point, this is V plus 3A point divided on A epsilon. And plus V will be joined, so I can take out it outside of the bracket. So plus P 3A point divided on A equals 0. So, and since the volume is not 0, we can finally to write the equation in the form, so it epsilon point plus, so I have the same multiplier in two forms, so I can call this like this, and here epsilon plus P equals 0. So this equation which we obtain, this is equation of it's better to say of matter. What is a matter? Just a second. Okay, equation of the medium. It's like this. So, what this equation allow to understand, allow to obtain? This equation establishes a connection between energy density and pressure. So, and as we will see, in principle, this equation can be obtained from the covariant derivative of tensor energy impulse. So we discussed it. Covariant derivative of stress energy tensor tell us and give us the conservation law. But for now, it's much more convenient to obtain this equation like this. So finally, we have now, okay, I will put here with a lambda constant. We have a 3 equation in principle with 3 unknown values. So it means that in which this value, this is scalar factor, this is energy density, and this is pressure. As a parameter, this is scalar curve, this is sign of the curvature of the space. But two of these equations are not independent equation, because, for example, this equation can be expressed through one of these. It's for a point of convenience to use it. So we need something else, and what we need to, to finally to finalize the system which we can solve, we need to use the equation of state. So in the form P equal some function of energy energy density. So when we speak about equation of state, sometimes it's really very complicated equation. For example, if you will consider the equation of call it, just a second, sometimes it's the equation of the generate electronic gas, neutron gas. It's really very long and complicated. Which is beautiful that the equation of state, which we will consider for cosmology, it's really simple. But of course, we need to understand what exactly we need and which exactly the equations we need to use and which matter is important to take into account in the, when we consider universe as a unique system. Of course, universe consists of a lot of things, but as we already discussed, we try to smooth everything and to try to consider which exactly matter put a lot of important or play important role in the total energy density. So, and in cosmology, we can consider this equation of state just in form P equal W multiply on epsilon, where W is a constant. Why? We will now a little bit later understand. Now I just write what exactly, and we will discuss it a little bit later why this is like this. So, for example, three important form of the matter which we need to take into account for the evolution of the universe. This is non-relativistic matter. That is non-relativistic matter. This is everything. This is including baryon matter. And sometimes when we speak about baryon matter, we understand that this is protons, neutrons, so this is everything, including electrons, there are leptons, but okay, it's the mass of electrons and leptons so small comparison to the comparison to the baryons, so that it's not important to speak about this. Okay, baryons. So this is planets, stars, gas, everything. When we speak also about non-relative matter, in principle, we can, in the future, when we will speak about this, we can also take into account such called dark matter, which is not baryon, but we for now we believe that it should be non-relativistic matter. So, and for non-relativistic matter, we use such called dust equation of equation of state equation of dust. So in sense that when we consider so huge scale, we consider that collision, so like a collisionless systems, that the object collide very rare, so they move, but can move, for example, but we don't consider the collisions. It's not important on the cosmological scale. Again, when we speak about cosmological scales, this is more than 100 megaparsec. The second, if we speak about non-relativistic matter, so it means that we also need to have a relativistic matter. And of course, the universe consists of the matter. By the way, when we speak about okay, it doesn't. Okay, so relativistic matter, it means in the first this is radiation. So this is photons. And for photons, we know that equation of states, this is 1 divided on 3 epsilon. So you can obtain it directly from the energy stress tensor for electromagnetic field. This is equation of state of emission. Photons, okay, photons. In principle, when we speak about relativistic matter, we also need to take into account neutrinos, which are also relativistic particles. So, and we will see that approximately it also can give this important part, not so important, because as we will see also relativistic matter and photons give not a lot of contribution, huge contribution, and total energy density for the present time. So also we can consider, so it means that W equals 0, here W equal 1 divided on 3. And also there is an interesting component, because if we will come back to the acceleration equation, Friedmann-Lemaitre acceleration equation, so I'll write it here again. A point divided A equal to point minus 4pg divided 3c square. So epsilon plus 3p, epsilon plus 3p. So we can see that this equation tells us something interesting, because it depends on what sign in these brackets. So, for example, if epsilon plus 3p more than 0, so this is positive, it means that p more than minus 1 divided on 3 epsilon, it means that this constant W more than 1 minus 1 divided on 3. What we will have in this case, in this case, A 2 point is negative. So we can see that in this case, Friedmann-Lemaitre equation tells us that universe will expand with deceleration. Beautiful. So, and in principle, okay, because we even intuitively can understand that if, for example, you have some gravitating solid sphere, and which is expanding. So the gravity will work against this expansion. So, and this expansion will be with deceleration. Sometimes when people like to speak about Big Bang, like this, you know, something was under explosion, I mean, universe, and some kind of representation of the evolution of the universe. And after this, consider this like a two-dimensional surface, and it's expand, but like an explosion in the atmosphere. And we also can see that explosion is in atmosphere, you know, it decelerates, so became slowly. Of course, it was the other effect, but in sense of the when we speak about gravitating system, it's understandable that gravity will work against this expanding solar and deceleration will be negative. But and also we can see that exactly the equation of states for relativistic and non-relativistic matter correspond exactly to this condition. So this is correspond to this condition. But if epsilon plus 3p less than 0, it means that p less than 1, 3 epsilon, which is strange, that we can see that the pressure is negative. So double V less than 1 minus 3. The acceleration positive. So, and it means that expansion will be with acceleration. So this is deceleration. This is acceleration. So, and okay, and this case is interesting, and I just in advance can say that the case with double V minus less than minus 1 divided on 3 called in general called as a dark energy. So this term was the first was used by Mitchell Turner, and when we speak about dark energy, this is something which create the phenomena of acceleration of the space. So this is the main point. Dark energy is something, and we need to clarify what is something to create the phenomena of acceleration. Universe. Acceleration of universe, we understand that we speak about space. So we have 10 minutes. Okay, and we will see that the case when double V equal minus 1, it means that pressure equal P equal minus epsilon correspond exactly to cosmological constant. So we will see it soon from equations that this is like this. Yeah, we can see even immediately. Look, I will let's to see that really we can coincide to cosmological constant coincide state this, so which correspond to the negative value of pressure. Look, if we will consider Friedmann limit equation, okay, equal 8pg divided on 3c squared epsilon minus k, okay, c squared divide a square, okay, we keep this r0 square plus lambda c squared divided on 3. So what we can see from this? Look, if I will do Let's consider that k equals 0, for example, flat space, and we can forget about the summand. Not so important. Okay, look what I can do. I can divide here on c square 8pg and multiply c square 8pg. 3 I already have. What in this case I will have? I will have 8pg divide 3c square. Okay, and inside I will have, once c will disappear, no, not disappear. So I will have lambda c4 divide on 8pg. Okay, now I can write Friedmann-Lemaitre equation in the form a point divide on a square equal, so for k, just for simplicity, just to simplify, you know, I can consider a flat space k equals 0, because for me the summand is not important. So I can write 8pg 3c square, and here I write epsilon plus lambda c4 8pg. So it's understandable that the summand, has a dimension of energy density, and I can call it epsilon lambda, just to clarify that this is correspond to lambda term. So what you can write, it will be, so epsilon lambda c4 divided on 8pg. Since lambda equal constant, the energy density also is a constant, because lambda constant. Okay, so, and we can immediately to see, so it means that we can consider the cosmological term as a some cosmological term as a some form of the energy, so which has such a properties that energy density is a constant during all time of the evolution. So this is definition due to the fact what we did in equation, and what we can clarify here. Immediately from the equation of the medium which we received here, look here, since look on this equation, since epsilon point, so the derivative equals 0, because is here, no, because epsilon lambda equal constant, we can see that from equation of the medium, we can see that we will have a point divided on a. Okay, let's put here 3. In case disappear. P plus epsilon equal 0. I will put here lambda as index and here lambda as index to just to show that I speak only about this kind of the energy or matter. So, and immediately from this, since if we consider that a point divided on a is not equal 0, so we obtain that p lambda equal minus epsilon lambda. So we obtain, you can see that cosmological constant we can consider as some form of energy, which a matter in general, which has a negative pressure, is a negative pressure. So you can write the definition. So cosmological constant, this is such a kind of component of the universe which has a constant energy density and constant pressure, which is negative, which has a negative value. And this component of the universe, if this component is present, so we will speak about this, will bring us to the fact that A2 point is a positive. So it will create acceleration of the universe. If we will consider the universe with only this component. Because in principle, as you already understand, since we have here, you know, this epsilon, we understand that in this epsilon, we need to put many, not many, but some components of the universe, which we have, non-relativistic matter, relativistic matter, and in principle, we can consider how they will concur with each other. Dark energy, non-relativistic matter, and relativistic matter. And we will see, so I have 1 minute, so I will analyze on this. And we will see that in past, for example, it was a very important role of non-relativistic matter. After this, non-relativistic matter, and later the dark energy. So unfortunately, our time is gone. So if you will have some question, please ask me. Otherwise, we will finish. Yes, I need to make. You have some questions?
Yeah, I have one question about our previous homework. So about solution as program. If I obtain inside program all Ricci tensors and with mixed components, with mixed index, with lower indexes, can I just send it and no, I already have answers.
Okay, did you obtain the final result for the yes,
no,
for
final,
the Ricci
no,
tensor?
final result is Ricci tensor. Yeah, I obtained it.
Okay, okay.
Oh.
You made it in Wolfram Mathematica.
Yes.
Okay, send me, I will look. Yeah.
Okay.
For now, I have only one student who sent me, who succeeded with this home task. So, and your second one, Sergei Popkov, yes, right? Who spoke just now?
No, that's
Simeon, sorry, Simeon. Sorry, I don't see your faces, and for me it's complicated very quickly to recognize. So, but again, remember that I give you only 1 week. 1 week, it means up to next Friday. Okay, so I would like to repeat that I will not allow to send me all solution of your home task before exam. So I'm waiting for your result. Okay, if you don't have any questions, if you have questions about home task, you can ask elsewhere about lectures too. No questions. Okay, in this case, see you on Friday. Thank you.